Furstenberg. Thank you.
Thanks. Yeah, so this is joint work with Somnath, Mrinal, Varun, Ramprasad, and Shubhangi. So the key question here is, are factors of succinctly represented polynomial succinct? Succinct. So what I mean is, so let's have a polynomial P, and it factors into Q into R. If P of X has a succinct representation, do the factors Q and R have a succinct representation? Now, what do I mean by succinct representation? So, we saw this in Robert's talk also, but let me repeat. So, this is a polynomial, and I can succinctly write it as a small formula like this. And this formula I can write down as like a tree with variables and constants in the leaf nodes and plus gates and multiplication gates in the internal nodes. And you compute, and we say this formula computes this polynomial, the above polynomial. When we just do this inductively, at each gate you compute what polynomials you get and you travel through it. And the parameters of interest for us will be the size of the circuit, size of the formula, which is the number of edges or wires you have, and the depth. The depth is the length of the longest path from leaf to node, leaf to the root, which is 3. And similarly, we have another model that is circuits. They're just like formulas, but for each we are allowed to reuse computation gates. So from a gate, for example, this plus gate, you can have multiple output nodes. Okay, so we can say that circuits have slightly more power than formulas. You can because you can reuse computations. And again, the parameters of interest are size and depth. So now let me rephrase the question I started with in this language. So I have a polynomial P, and Q is a factor of it. Suppose I told you that P had a size S circuit, then can I say that Q also has a small circuit? So by small, I mean that there is a polynomial blow up in the size. So I'm okay if the circuit of Q is at most poly in S, D, and N. And I can now ask the same question on restrictive models. For example, I can ask this question on formulas. I can say if there's a size is formula, does the factor have a small formula? I can ask if I have a sizes circuit with depth delta. So you can think of delta as a constant here. And then I can ask, does the factor have a small formula? A small circuit with a small blow up in depth. So size is poly STN and depth is just delta plus some constant. Right? So turns out that the first question, the first statement here was known to be true for a long time. So this result is from Kaltofen and Trager. So suppose, we have polynomial P and Q is a factor of P. Then if you knew that P has a small circuit, then Q has a small circuit. Okay. And this work, what we show is this theorem of Kaltofen, Trager is true in the more restricted setting also. So if so the setup is same. We have a polynomial P, Q is a factor of P. If P had a size S circuit with depth delta, then Q also has a small blow up in size, poly STN, and the size depth is delta plus over 4. Similarly, we have the same result over formulas. So if P has a small formula, then the factor also has a small formula. Okay, so now I'll prove this theorem. We have a special case of it. So yeah. You can think of algebraic, branching programs, for example. One maybe model of, one naive way you can reference the polynomials by is monomials, like by its monomial representation, sparsity. But it turns out that in sparsity, this is not true. So there are examples where the factor can have more, like super polynomially many number of monomials than the initial polynomial. But in these models like formulas, constant depth circuits, branching programs, also this class of V and P, it's all closed under factorization. So it's true over, so if you're on field of characteristic 0, it's true. If the characteristic is larger than D, it is true. If the characteristic is much smaller than the degree, then we almost have this in the sense that, so when characteristic P, if P is much lesser than D, if I give a circuit for G power P, we don't know how to get circuit for G. So up to computing the power of the characteristic, I know how to get the factors. Right. Yes. Okay. So let's try to prove this theorem. So I'll think of my polynomial to be on n variables, and I'll treat the last variable as special. I'll call it y. Okay. And I'll assume some things. I'll assume that this polynomial is monic in y. That means the highest degree term in, like, if I look at the highest degree in y, its coefficient is 1. And I'll also assume that if I substitute all the x values with 0, p of 0 comma y is square free. As in, if I look at this univariate polynomial 0 comma y, it factors into linear factors and there are no repeated factors. Okay. These are easy to handle, and I mean, a general case of factorization can be reduced to this, so I don't want to spend time on that. And what we'll do is we'll try to reduce a general multivariate factorization problem into a bivariate instance. So I'll replace each x1 to xn minus 1. I mean, I'll multiply t with all of them. And I get this polynomial f t comma y. And I'll work with this polynomial, and we'll see that it has all the properties that I mentioned here. So it's monic in y, and it also be square free. Okay. So maybe to see the ideas involved, I'll just look at an example here. So of an f t comma y. Let's work with this polynomial. This is some polynomial f t comma y, and its factors are y square plus 2ty minus 1 and y square minus 2ty minus 4. Okay. It is monic. So if you look at the leading term in y power 4, it is 1. And if you substitute the value of t, you'll notice that, I mean, this term zeroes out and this term zeroes out, and this factors into linear factors with no repeated roots, so it's square free. And so what we can see is, from each of the roots we have here, we can get a power series root for f t comma y. So what do I mean by that? So f t comma y will factorize into linear factors where each of the roots are essentially power series in t. And if you look at the constant terms of each of the power series, so the first one, it is 2, and that's lifted from the y minus 2 here. So each of the roots here, we can lift into a unique power series. And this is a well-known fact, and all the non-degenerate conditions I said that it's square free, it's monic, or required for this to be true. Okay. So we have this. And okay, so now what do we have? We have this polynomial, it factors into these things, and we have another factorization in terms of power series also. And what we have is these power series can be used to get these factors. So if I multiply this things marked with green here, we'll notice that we'll get this factor. And if I multiply these power series roots, I get this factor. Okay. So what I'm saying here is that f t comma y, it factorizes fully in the power series, and each of the power, and if I look at its actual factors, they can be obtained from multiplying the corresponding power series factors in this representation. Okay. This will give you a high level view of, okay, how should we go about a factorization problem. Okay. So let's go back to our settings. So we have f t comma y, g t comma y. G, let's say the factor of f. Now I'm promised that f is a small constant depth circuit. I want a small constant depth circuit for g. So as you saw earlier, if I assume nice things, then f t comma y factorizes fully as y minus phi I of t, where phi I of t are power series in t. Okay. And as you noticed earlier, g t comma y will be product of some of the power series roots for some non-empty subset S of, okay, this should have been D. basically I pick up some of the power series roots, multiply them, I get G. So now to get a constant depth circuit for G, all I need to do is, if I could get, let's say if I could get a constant depth circuit for this power series roots, I could get a constant depth circuit for G. And okay, one thing to notice is that on the right hand side, we have this phi G of t, which is a power series, an infinite object. And I multiply all of them and I get something of constant degree, of bounded degree. So what I can do is, instead of multiplying phi G of t, I can just extract the top d terms of it and multiply. Because anyways, the higher degree terms are getting cancelled out and they don't show up here. So I'll define this thing of homogeneous up to d of phi G of t. That basically means I want to extract the first degree d terms of phi G of t. And all you notice is that gt of y is essentially, I just have to multiply the top degree d terms of the power series. And this multiplication might lead to some higher degree terms. I want to just remove them out at the end. So to get our hands on gt comma y, all I need to do is get my hands on this expression here, homogeneous up to degree d of phi j of t. And if I could get a small constant depth circuit for all of these things, then I can get then getting a constant circuit for gt comma y is easy, because I just have to multiply the whole thing and do an extraction of coefficients, this of the top degree d coefficient. All of this can be done in constant depth circuit. Okay. Now, how do I get my hands on these objects? So this turns out, for this we go back to an old theorem by Furstenberg. So this paper of Furstenberg was about algebraic, it's titled Algebraic Power Series over Finite Fields. And proposition 2 of the paper has a closed form expression for the power series. And this will be crucial for us to get our circuit. So, okay. So we have a pt comma y, and phi of t is, phi of t is the root of this. And we have some non-degeneracy conditions here, and we have a closed form expression for phi of t in terms of p. So, there are some terms here like p ty comma y and dou y of p ty comma y. But notice that if I had a small constant depth circuit for p t comma y, I easily get a constant depth circuit for this and for this. And that is the intuition here. Like, once I have a constant depth circuit for my original polynomial, these expressions are easy to compute, and I get a handle on phi of t. So let's maybe dig deeper. So I'm now defined this d. So okay. So this d basically means it's a diagonal operator. Essentially, what it means is I have a power series with a lot of x power I, y power j. All the diagonal operator does is it extracts out only the I part out of the power series. That detail is not crucial, but what is crucial here is that once I have a small circuit for p t comma y, I have a small constant of circuits for this entire expression and also with the diagonal operator. What we see is this expression can be further simplified into a nice closed form expression. Yeah, when you look at it, it looks like a complicated bit of expression, but the main key point that I'm trying to convey here is that the power series root has a simple closed form representation in terms of the original polynomial. And all of these things I can represent easily with a small constant depth circuit. Okay. Now, okay, I won't be proving these things, but I'll be using this to maybe, okay, this is a key theorem that we want to show. The key theorem, the thing that we want to show is that I have a polynomial p, and I have phi of x that's a root of the polynomial. And all I want to say is that if p had a small circuit C, then if I wanted a small circuit for the power series root, and this theorem says that I do have it. So I have a circuit for C dash that is just a poly blow up with respect to the size of C. And the depth of C dash is just depth of C plus O of 1. Right? Okay. How am I doing with time? Yeah, fine. Okay. I don't know if I want to do the proof of it. Okay. I will not be proving the, okay, I have a proof of this, but maybe I'll hit this. Okay, or maybe we can prove it. So essentially what we want is we want a small circuit. So here I'm working with a general P x comma y, where x is a variable like x1 to xn. I want to come back to bivariate case. So I work with fty by replacing, by multiplying t to all the x variables. And I notice that the power series root of ft comma y has a small expression, as a simple expression that comes from Furstenberg. And the only thing I notice is that in order to get the top degree d terms of this power series root, I need to sum up my expression here only up to the first 2d terms. So I won't go into the details, but that's all we will need. So yeah, just stitching it all together. So I started with the polynomial p, that's n variate and degree d, and I wanted a factor q of p. Let's suppose that p is computable by size s and depth delta. And what I do, first thing I want to do is I want to reduce a bivariate case, because the Furstenberg statement was in a bivariate sort of setting. So I want to go back to that. So I multiply each x variable with t, and I do the same with q. Sorry. So I have f and g now. Now I have, suppose I'm promised, so since p has a small constant depth circuit, I'm promised that f has a small constant depth circuit, and I want a constant depth circuit for g. So as we saw, f factors into power series roots. And we saw earlier that to get our hands on g, we need to compute the top degree d terms of the power series phi j of t. And by Furstenberg's theorem, we know that this expression, getting the top degree d terms of phi j of t, has a small constant depth circuit. It has a circuit of size at most poly STN and depth delta plus O of 1. And to get my hands on gt of y, since I have a small circuit for this, I just have to multiply it out with y minus this, and and do an extraction at the homogeneous extraction at the top. All of these are preserved under constant depth circuit, so I get a small constant depth circuit for gt of y. Okay. So I'll just conclude with some application. So I mean, I proved this. I mean, this was proven. This theorem was stated earlier for constant depth circuits and formulas, but it turns out that the same proofs goes over for like the question Pala does. It goes over for a lot of the other models also, like circuits, branching programs, formulas, constant depth circuits, and the class VNP, like this exponential sums or algebraic circuits. And there are some other applications. So maybe I will not mention them. So if you know about this, so this is improved algebraic hardness randomness trade-offs. And yeah, it also gives a simplified proof for getting a deterministic algorithm for factoring constant depth circuits, which Varun will talk more about. Thank you.
Questions?
No, so all I wanted to do was I wanted to show that there exists one, so I don't care about it. But if I wanted an algorithm, that would be a key problem. So Varun will be talking more about it.
Okay, let's thank Shanthanu.
Am I audible?
Yeah. So